of the generation term versus the temperature. And on this same scale, we can put the slope of the heat removal term. So which region is stable? So the criteria at the critical point what do I put here?
The straight lines above this.
This isn't that. There's no straight line over here.
What are you plugging over here then?
Greater than.
Is that for? Yeah, isn't that the one on the left always like a straight line, right?
No, this is constant. This doesn't depend on temperature. There's no temperature in here.
On the other graph, doesn't S star being UGDT equal to the RDT at 2 points because there's the ignition point and the other point?
Say that again. You're saying at the tangent point, the two functions are equal to each other at 2 points?
Yeah, for that.
Yeah, there's still two steady states. 3 and 2.
So then,
But you have to solve both that equation and another equation at the same time to find the tangent point. So what's the second equation that you solve for?
wait, it's T equals T, but then why, like, which one are we looking at on this graph? That's just what I'm.
This is plotting S, which is the slope of G, the heat removal term, at a specific temperature. So this isn't how does the slope change with temperature. This is what changes this slope. And so one of the things that's in this equation is Tc. And so now we can plot, there's many ways to make these stability plots because there's many factors that show up. But one thing that we can do is we can plot the slope versus Tc. So depending on how we change Tc, the slope at this point will change. So this region is stable. This region is unstable. And that's basically saying that you want the heat capacity times 1 plus kappa to be greater than this S function.
Where is CP left with kappa there? It's not S star.
I mean, they have the same units. You just imagine that you can put them both on the same axis. I mean, it can be anywhere. It's just these parameters. If you plug in these parameters and you end up here, then you're in the stable regime. If you plug in the parameters and you end up here, then you're unstable. It's not a function of Tc.
Right, so it's just a constant.
Yeah, right. So this is just showing a parameter
Is this
space.
a straight line? Yeah, I have the same question last time. Where's CP, parentheses 1 plus K?
Yeah, you can think of it as a straight line, but yeah, that's one way to think of it.
But what about under the straight line, above the curve?
So that's just telling you that if I give you a heat capacity and a kappa, then it still depends on what Tc is, whether you're stable or unstable. Because if you're at a low value of Tc, this point is stable. If you're at a high value, this point's unstable, right? But I can be here, and all the points are unstable. So all that this is showing is that this inlet heat capacity affects whether or not you're stable. So does kappa, and I can put those up if you guys want me to. We've been using them all day today, but I didn't put their definitions back up. That's the definition for kappa and the critical temperature. So if my feed composition changes, will that affect the stability? And why?
That's the heat capacity.
Yeah, because the inlet heat capacity is going to change with that. So the point is that anything that causes this, anything over here where I'm decreasing this value, I run the risk of decreasing it to the point where I'm no longer stable, which is here. You have ignition, which occurs Okay, any questions?
From before, if you want to get to 5 and start it from the 1, would you heat up to 4 and then go?
If you want to get to 5, yeah, you need a really good temperature control. You need something where you can heat it up to 5, but then you got to be able to cool and keep yourself at the temperature, the desired temperature of the reaction.
You would have to force it up to that, right?
Yeah.
The reaction wouldn't be able to go to it normally.
Yeah. You'd have to pump in the right amount of heat in order to get to that temperature and then back off as soon as you got to that temperature because you're at steady state. So, I mean, you still got a liquid at the end of the day, right? So you can force it to get there, but that's where you have to have really good temperature control over the reactor. I mean, you can do that. I mean, there are people who have done this experimentally and can probe all of these data points. But the point is that once they hit that steady state value, they know that if they fluctuate, they're going to hit one of the more stable data points. But it doesn't stop you from ever getting to that steady state. Just with a normal startup routine, you wouldn't see it. Any other questions?
Would there ever be any point to run it at that?
I mean, if you really needed that conversion and that temperature for some reason, you know, I mean, like the point was made earlier, what if you don't want to run up here? Maybe you can't run up here, but this is too low conversion. But I mean, I don't think anybody would want to set up a reactor where some perturbation is going to really stress their control scheme. So I think one of the homework problems, I think just one, deals with an explosion. So this is one of the things that can cause reactors to explode, is people operating near these ignition points and something happens to the feed or the operating temperature and it causes an undesired temperature to be reached within the reactor, which causes an explosion, usually because some reaction you don't want occurs at that temperature that results in a dramatic release in pressure, and your containment vessel can't hold that release of pressure, so boom. Like I said, that's one of the homework problems. So, you know, think carefully about that homework problem, or let me know if you operate a reactor so I can not live near you when you get out into the real world.
You have high hopes for us.
I said or. I recognize that you might think carefully about the homework, but if you don't, I want to know. All right, so let's look at an example. We have an irreversible reaction. A goes to B, and we're doing it in a CSTR. And it's asking us to evaluate the runaway conditions and find ignition, extinction points. It's a jacketed CSTR. $500 liters coolant comes in at 300 Kelvin and it leaves at 300 Kelvin. The flow rate into the reactor is 10 moles per second. It's pure A. Concentration, 2 moles per liter. And the feed temperature is 300 Kelvin. The rate, first order, oh, that's what that says. Liquid phase. Okay, so what's the material balance, aka design equation? Volume of a CSTR is equal to what? The rate equation, I've already put on the board. What about stoichiometry? Concentration of A is equal to the flow rate of A divided by the volumetric flow rate